The topic of my presentation is the relationship between the core and modified cores of a dynamic game. The table of contents is as follows. We consider the cooperative cases of a dynamic game, and we take the core as a cooperative solution of the game. The core has good properties, and any imputation of it is undominated, but it's not usual to get a strong time consistent result for the core. Fortunately, there exists a strong time consistent core result for the modified cores, which is obtained by making linear transformations. However, the modified core is quite different from the initial core. If the modified core shares a common imputation with the original core, we will got a good result. Since we may got a strong time consistent result for the intersection between the initial core and the modified cores. Therefore, the presentation is more about the relationship between the original core and modified cores. We start with the dynamic game, which is denoted by gamma of x1 capital T, where x1 is the initial state of the game, and the game stages is denoted by the special T. And at any stage, the player I will choose an action which is denoted by UI of T, and let U of T be the action profile at stage T. The dynamics is described by a function where x of T is the state at stage T, and U of T is the action profile at this stage. The strategy of player I is denoted by vertical UI, which assigns action to each stage and each state. And the strategy profile is denoted by the vertical U. Given the strategy profile, we are able to got the trajectory in the dynamic game, which is denoted by gamma. It is determined by the dynamics. And the pair to player I in the game is defined as follows, which is a summation of stage pair of hi over T from 1 to capital T. And the pair function of player I is denoted by G sub I of U. We suppose all the players will cooperate with each other, and the maximum total pair is as follows, where U star is the cooperative strategy profile, and it will determine a cooperative trajectory, X star, according to the dynamics. For convenience, we denote the cooperative counterpart of the initial dynamic game by NV1. There are many ways to determine the characteristic function, and for example, we can use the von Neumann-Monst approach to determine it, which is as follows. And in the subgame gamma of x star of T, we can define the cooperative subgame similarly, which is denoted by NVT. Given the cooperative trajectory x star, the linear transformation, which is introduced by Peter Xiang, 1993, of the initial game is defined as follows: V hat T of S is a summation of such a quotient, where the summation of HI is the total stage pair at stage tau, and the quotient V tau S over V tau N can be viewed as the relative worth of collision S in the subgame N V tau. And we took this summation as the new characteristic function of the modified game. And note that this linear transformation does not change the worth of a grand collision. That is, V hat T of N is always equal to Vt of N. And for convenience, let Vt sub M be the modified characteristic function in the subgame gamma of x star of T, after making this transformation m times. And if m tends to infinity, we may got a limit actually. According to Peter Xiang et al., 2017, the limit v bar t exists. If the limit v bar t exists, it will be the following formula. But it sometimes does not exist. Our first result gives the sufficient and necessary condition of the existence of such a limit. Proposition 1 shows that when the limit v bar 1 exists, if and only if we have these inequalities and such a condition. The first condition means that the words of ground collision must have to be always the same sign. It means that they are always positive or always negative. And this condition means that the worth of ground collision n in a subgame is at most twice its worth in the previous subgame. And note that when the limit v bar 1 exists, then the v bar t exists for any subgame along the cooperative trajectory. And now we can talk about the relationship between the cores. Suppose VT of n is not increasing in t and positive, it holds that if we have such a relation, the initial core will contain the modified core, after twice transformation, and will contain the limit core at last. And when the comparison sides are inverse, the core inclusion, as you can see, will be inverse too. And the core will be of the same if those quotients are equal. This is for the general modified games, and for the limit cases, as we can see, when the limit v bar t exists, if Vt of n is positive, and the initial core C of Vt and the modified core C of v bar t are not empty, it holds that the initial core will contain the limit core if and only if this quotient is less than or equal to such a quotient. And when the comparison size is inverse, the core inclusion is inverse here. And the core is the same if they are the same. Now let's consider a specific games. We suppose the cooperative cases of the dynamic game is described by the linear symmetric games. It means that the characteristic function Vt of S is of such a form. And in the linear symmetric games, when the core is not empty, the Bt is always negative. So we always consider cases when Bt is negative. The corollary one directly comes from the proposition 1. It says that when the characteristic function Vt of S is of such a form, and the worth of ground collision is not increasing in t and always positive, it holds that we have such a core inclusion if the quotients are of the same relation. And the core inclusion will be inverse if the comparison sides are inverse here. And the core will be of the same when those quotients are equal. And for the limit cases, when the Vt of n is positive, and if the limit v bar t exists, then for any given stage, it holds that the initial core will contain the limit core if At over Bt is larger than this quotient. And the inclusion will be inverse when the relation will be inverse too. When you want to go to the relation between the initial core and the limit core, you only need to consider the relation of such two quotients. So it's really it's really easy to check. And next, let us consider a class of linear state games, which is studied in set curve until 2020. In this game, whose dynamics is given by following formula. And note the game is start with x0 instead of x1 here. The CGP are as follows. And when we introduce the following functions of the following functions, the cooperative trajectory can be right of such a formula. And the characteristic function of such form. Now let's perform a 3-person game and specify the parameters as follows. Various only parameters E10, E20, E30 vary. As you can see in figure 1, it shows that the initial call, which is circled by the black borderline, intersect with the modified call. And the twice modified call is out of the initial call. And the limit call, which is pointed here, is also out of the initial call. But in the figure 2, you will see that the initial call contains the modified calls, and the limit call is included in the initial call. And the figure 3 shows a total different cases. The initial call does not intersect with the modified calls at all, and the limit call is out of the initial call. Our theoretical result is when the limit characteristic function v bar 0 exists, if we have such inequality and such a condition for every collision S, the initial call will contain the limit call. And moreover, when pairs are symmetric, those two conditions are automatically satisfied. So we have the result that the initial call will contain the limit call for NT. To summarize, we extend the conditions which leads to the convergence process based on the transformation rule. And we also got sufficient conditions for the co-inclusion. And at last, we consider two specific games and show their co-inclusion. That is all. Thank you.
Okay, thank you. Anybody has questions?
Can I ask a question?
Yes, yes.
How to apply the modified characteristic function in reality?
Excuse me, can you repeat the question?
In any time, the players can calculate the future reward, and they compare real characteristic function.
Yes. After
your modification, you have new characteristic function, but how to apply it? Because it is not real reward. It is some artificial reward. What is the sense of this function?
For example, in a subgame, along the cooperative trajectory, in a subgame, subgame NVT, the worst of collision S is VT of S actually, not V hat T of S, and the collision S will consider what he will get at the state xt star at the terminal, not terminal, at the current state xt star, and it will suppose that it may want to get the how to say, the total stage period at this stage is the summation of HI. And the collision S may claim for itself the share which is proportional to the worth of collision S. And we take the summation, the worth of the collision S. I'm not sure if I explain it clearly,
Yeah,
but actually,
I understand the formula, but what is the philosophy of this formula?
Philosophy.
Yes. So that is artificial reward of coalition S. That is not real reward. That is modified reward. So how you can explain people from coalition S that they need to use this characteristic function?
Actually, the when we make a linear transformation over the initial character function, it changes the what's the collision S actually, and maybe the modified call we got is quite different from the initial call. But what we pay attention to is the intersection between the initial call and the modified calls. If the intersection is not empty, we only consider the empty set and take it as a new solution. So it doesn't matter the we had TFS different from the initial was collision S. The important thing is that the intersection of these two calls is not empty.
Okay, thank you.